Hello, today starts graphing logarithmic functions. So let's put a title for our notes, 5.5, graphing. Logarithmic functions. And this is going to be 5.5, day 1. So before we get into graphing, we need to recall our general formula. So let's say recall. The general form will be f of x equals a times log base b of x minus h plus k. And I would highlight that so it stands out in your notes. So grab your highlighter. Remember, for me, I don't want it to not be able to print nicely if somebody needs this printed. So what I box is highlighted. Let's first talk about graphing characteristics. So graphing characteristics. First of all, as we discussed, all logarithm functions have a vertical asymptote, but now we can actually be a little more specific about where that is. So the vertical asymptote is going to be at x equals h. If b is greater than 1, the graph is increasing. Left to right. If b is between 0 and 1, graph is decreasing. Left to right. So if we draw ourselves a quick little picture here, let's first look at b greater than 1. So for example, log base 5 of x. That b value is greater than 1. I have no horizontal shift, so that means my vertical asymptote would be at 0. And left to right, this graph is increasing. Left to right. If b is between 0 and 1, so for example, log base a half of x, let's now sketch that. My vertical asymptote will still be at x equals 0, but now the graph is decreasing left to right. Let's now discuss domain restrictions. So if you are using your highlighter, let's keep track of our titles. So first, we just discussed graphing characteristics. Now we are going to discuss domain restrictions. As we discussed when we were solving logarithmic equations, we have a domain restriction because there is a value of x that has to be excluded, and it's where that asymptote is located. We can't take the logarithm negative or 0. Let's explore the reason why a little further. A positive base raised to a power is always positive result, never negative. So for example, if I try taking, let's say, log of negative 5, and we said that that equals some number, that would mean, remember that this is log base 10 if you don't see something, that means that 10 to a number can equal negative 5. That will never be true. Same if we tried taking log of 0 and said that that equaled some number. Once again, this is base 10. So that would mean that 10 to some number can equal 0. There is no value that would ever make that true. So that is why we cannot take the logs of negatives or the log of 0. We need to restrict any value of x that would create a negative or 0 in the argument. Graphing examples. Stay consistent here with my titles. We are going to want to input numbers that make the base the same, or give a value of 1 if possible. If we're using the calculator, so if using the calculator, and it is not a common or natural log, use the change of base formula. Let's get into our first example. Number 1, the directions are to graph f of x equals log of x. No calculator. So if you have your calculator out, close it. No calculator. So first let's set up an input-output table. Leave a little space off to the left because we're going to be doing a little bit of notes over there. Not a ton, just a little bit. So if we go back to the graphing notes we just wrote, it says that we want to input numbers that make the base the same or give a value of 1 if possible. So for me, right now I'm dealing with log of x. I definitely need to remember that this is actually log base 10. So we're going to go back to our very first log properties. So once again, let me just say one more time. Input numbers that make the base the same or give a value of 1 if possible. So I'm not exactly sure what I want to choose for x yet, but I do know that it would be really nice if I'm dealing with log base 10 to be taking log of 10. So that gives me my first value of x, because log of 10 equals 1. Remember, this is log base 10 of 10, inverse properties, that cancels and equals 1. What would be another nice value? Well, this was log of 10 to the first, and that got me 1. I can continue this pattern and say, well, let's say log of 10 squared. Log base 10 of 10 would cancel. But what is 10 squared? Because we have to decide what value goes in the table, right? So 10 squared is 100. And again, we chose that because I can rewrite 100 as log of 10 squared, which equals 2. No calculator. We can also consider log of 10 to the negative 1, where recalling our exponent properties, 10 to the negative 1 is 1/10, so super close to 0, but not exactly 0. Log base 10 of 10 would cancel, leaving behind negative 1. And then the only part we haven't considered yet is inputting a number that makes the base the same or gives value of 1 if possible. Well, we've done 1, so I take that back. We took care of that. What if we took the log of 1? This is the property I meant to say. Remember that log of 1, no matter the base, will always result in 0. That was a property we had at the beginning. So if I were to rewrite my little table without all of the work in it, I now have these ordered pairs. 10, 1, 100, 2, 1/10, negative 1, 1, 0. So I literally just simplified the work we did here down to this table with 4 ordered pairs. We are now ready to graph, so let's sketch a quick graph. And from my table here, I see that I'm not graphing any negatives, nor would I expect to for this one, because in the argument it's just log of that value, so we would never choose a negative value to plug in, it wouldn't exist. And if I consider how far I need to get, if I look at my x values, my largest x value is 100. So maybe I choose to count by tens, so that'd be 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then for my y values, 0 to 2. So I can count by ones, 2, 3, 4, 5. So it's going to be a rough sketch, but we still want it as accurate as possible. Our asymptote is going to be where? Well, recall, the asymptote is located where? Vertical asymptote at h. So it's going to be inside the argument. When I look here, inside the argument, I just have x, or you could see that as x plus 0. So my asymptote, or x minus 0, we want to stay consistent. Asymptote will be at x equals 0. If you have your highlighter, maybe use your highlighter to do your dashed line. right on the y-axis so it stands out. It'd be nice if we label that x equals 0. And now let's carefully work on plotting our ordered pairs. We've got 10, 1, 100, 2, 1/10. Ooh, I need -1. So 1/10. So that's super close to 0, but not exactly. And then we also have 1, 0. So again, if this is 10, 1, 0 is going to be roughly right there. We're ready to sketch the graph. Make sure we're using pencil. Remember, super close to the asymptote, but we'll never cross. And our graph is complete. Let's state domain and range. The range of logarithmic functions will never have a restriction. I come in from the bottom, I hit an arrow. I come in from the top, I hit an arrow. Our domain will have a restriction. All logarithmic functions have a domain restriction. Here we need to say, let's see, I come in from the left. Notice, there is no graph that will ever be here. None whatsoever. So I come in from the left, I hit 0, but it'll never equal 0. I come in from the right, I hit an arrow, 0 to infinity. Taking a look at number 2. Graph f of x equals natural log of x. Remember, we're going to leave a little space off to the left to track some of our thoughts. So if we look at our previous example, we worked towards having an exponent of 1, 2, -1. Let's see if we can use that same reasoning here. What happens if I take, and this is where pencil is nice so we can kind of jot some notes, natural log of e to the first power. Remember, we're looking to have the same, to have the base and what we're taking the natural log of match, because then it cancels. Natural log of e will cancel, leaving 1 behind. So if I let x equal e, we get 1. What if I take the natural log of e squared? Well, natural log of e cancels out, leaving 2 behind. And for that, I plugged in e squared for x. Next, let's see what happens if I take the natural log of e to the -1. Well, natural log of e will cancel, leaving behind -1. And for that to happen, I plugged in e to the -1. For our fourth point, let's use the log property when we take the log of 1. Natural log of 1 automatically gets me what? Automatically gets me 0. So if I take the natural log of 1, I get out 0. Once again, by the way, no calculator. So if you were about to use your calculator to figure out what these are, don't do it. We know, or we should know, that e is approximately 2.8. So I know that that's going to be 2.8 comma 1. That means that e to the negative 1, which is the same as 1 divided by e, gets me 1 divided by 2.8. That's pretty close to 1/3. And I know how to graph 1/3 because I know 1/3 is 0.33. Remember, our sketch is going to be approximate. So notice how I'm able to use my prior knowledge to graph what might seem like you have to have a graphing calculator, and that's not actually the case. 3 points is sufficient for graphing, so I'm going to use this one, and this one to graph. I'd actually ask that you pause and try the graph on your own. I'm going to go with a 5 by 5 graph. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Press pause and you finish your graph, and then we'll see if we match. Press pause now. So I look and I see that x is by itself as the argument, which means my vertical asymptote will be at 0. Again, if you have your highlighter, use your highlighter. 2.8, be helpful if I finish this. 2.8 comma 1. So I'm going to go 1, 2, almost 3, not quite. 1. Then we've got 0.33 comma negative 1. So this is 1. So 1/3 is kind of like right there, down 1. And then last but not least, 1 comma 0. That is sufficient to sketch my graph. Let's discuss the asymptote, domain, and range. Try those on your own for a second. Go for it. What's the asymptote? And what's the domain and range? My asymptote, as we discussed, is at 0. The range is all real numbers. My domain, 0 to infinity. So my vertical asymptote is what affects the domain. Number 3, let's step it up just a little bit. Graph y equals log base 1/3 of x minus 1. Notice I do not have parentheses grouping this negative 1 into the argument. So if it helps you be crystal clear, if I gave you something like this, feel free to add your parentheses right there so it's very clear to you that this minus 1 is not part of the log argument. Let's set up our table. Once again, leave a little space off to the left. So I hope we are kind of seeing a pattern. In number 1, coming back to number 1, it was log of x. So 10 was my key number. 10 to the first, 10 squared, 10 to the negative 1 for what I choose as my input values. For number 2, this was natural log, which, as we recall, is technically log base e of x. And then notice, powers of e became my inputs because nice things happened as a result when I calculated, since log base e of e, or natural log of e, cancels. So applying that same thought to number 3, I see that I have log base 1/3. So what's going to be my go-to value? Well, let's start with 1/3. Again, no calculator. So leave a space and let's do the math. Log base 1/3 of 1/3 minus 1. Well, log base 1/3 of 1/3, what does that equal? 1. This minus 1 is still here, and we get 0. Now, if I try doing 1/3, so we just did 1/3 to the first power, right? If I try doing 1/3 squared, that's going to be a little ugly because we're going to get 1/9. And not that it's impossible, but it's going to be a little messy. So maybe we say, let me take a step back from that and say 1. Log base 1/3 of 1 minus 1. Using our properties, what is log base 1/3 of 1? I'm hoping we're all saying 0, and then minus 1 is still there, so I get -1 as an output. Now let's revisit what do we do next, because we still need a couple more points. Well, log base 1/3 is connected to 3. In our minds, we usually connect 1/3 as having a relationship to 3, since 3 is the reciprocal of 1/3. So let's just play around with what happens if I take log base 1/3 of 3. That minus 1 is still there. So I'm trying to consider, what is this? What does this get me? Well, how can I write 3? Oh, I'm going to pause the video for just 1 second. And I'm back. I can't rewrite 3 with any kind of base that would help me make sense of this. So maybe I step back into my prior knowledge and I ask myself, log base 1/3 of 3 equals some number. But I'm trying to figure out what that number is. So I remember that I can take 1/3 and rewrite this as 1/3 to the x equals 3. So what exponent would force 1/3 to flip so I get the reciprocal of 3? And that math fact is 1/3 to the -1 equals 3. So log base 1/3 of 3 equals -1 minus 1, I get -2. Let's work with multiples of 3 and see what happens. So the next multiple of 3 times 3 is 9. So let's work it out. Log base 1/3 of 9 minus 1 equals what? I'm breaking my own rules about space, so let me slide that down a little bit. Well, same idea. Let's use our prior knowledge of problem solving. I'm trying to figure out what log base 1/3 of 9 minus 1. Oh, no, didn't mean to write that. Equals some number. I'm trying to figure out what log base 1/3 of 9 equals. So I'm going to use my ability to rewrite this in exponential form to help me out so I can see it a different way. That's 1/3 to some power equals 9. Well, 1/3 to the -1 got me 3. So 1/3 to the -2 gets me 9. That means that that's -2 minus 1 equals -3. And as I was working on these little green notes, I am now remembering that on the front I had told you if it's not a common or natural log, use the change of base. So I apologize, I kind of got on my little no calculator kick, but I don't regret showing you how to do this without a calculator. With a calculator, since this is log base 1/3, remember that we can use change of base. So in your calculator, go ahead and do log of 3 divided by log of 1/3. Make sure you use parentheses. And you should get a -1. And then you can use change of base here. It will be log of 9 divided by log of 1/3. So pause for a second. And if we were getting a little concerned about this algebra, I still hope we can follow the algebraic reasoning as to why this worked. But know that if it's not log base 10 or natural logarithm, you will be able to use a calculator. So take a second and do log of 3 divided by log of 1/3. We should get out a -1. And then log of 9 divided by log of 1/3, and we should get out -2. Now that I have my table of values, which is right here, let's sketch the graph. So I see that if I look at my values, my x values go up to roughly 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And my y values, I actually don't have any up here to consider. So 0, 1, 2, 3, 4, 5. Let's plot those points. So 1/3, asymptote first. Sorry. Vertical asymptote at x equals 0, because once again, we have nothing being subtracted from x inside the argument. So x equals 0 is my asymptote. 1/3, comma 0 is going to be a little bit past 0, and the y value is 0, so I don't go up or down anywhere. 1, -1, 3, 1, 2, 3, -2, and then 9, -3. So notice the difference in shape between numbers 2 and 3. Number 2, e is greater than 1, right? E is 2.8. So when e is greater than 1, it's increasing left to right. Here, log base 1/3, b is between 0 and 1, decreasing left to right. Last example is number 4. So f of x equals 2 times the natural log of x plus 4 minus 3. So let's set up our xy table. And someone's at the door. Give me 1 sec. All right, I'm back. Apologies. So here I've got natural log, which technically is part of that note with natural log or common logarithm. But notice, I've got x plus 4. So the only thing I can do without a calculator would be to figure out what would make the inside be 1. What would make this argument equal 1? Well, I see x plus 4, so I know that if I plug in a -3, so let's see what happens. It's going to be 2 times the natural log of -3 plus 4 minus 3. -3 plus 4 is 1, which is what we expected. What is natural log of 1? Natural log of 1 is 0. So I get 2 times 0 minus 3, which is -3. So I know that this is -3. Past that single value, we're going to have to use our calculator. So take out your calculator and input this into your calculator. Then look at the table. For 2 or 3 more values. I'm going to leave finishing this graph for you guys. I'm not even going to sketch it. You finish the sketch, and I will check in with you tomorrow morning to see how the sketch went. And we are done with our first day of graphing notes. Good job, and we will be practicing tomorrow. So don't forget, yes, you're done with the video, but please input this into your graphing calculator. Make sure you use parentheses. Get some more values here that are easy to graph, and finish your sketch. And just like before, asymptote, domain, and range. See you guys in the next class.